Welcome to another video. This video is about hexadecimal systems. In last video I covered binary system and binary to decimal, decimal to binary systems, and I told that understanding binary system and arithmetic of binary is important because the the section that is coming next in different videos is on arithmetic operation. So we are now on hexadecimal. So why we use hexadecimal? First of all, I don't know if I explained that in the previous video, but the main reason is, well, actually I have it here. Um, we'll just use it in an example, but just to tell you, this one is 24-bit binary number. Let's say we want to store it in memory, want to move it somewhere, or want to um, um, translate it or express it in some way, or we want to understand what it is. Writing numbers like this we can make mistake. It's hard to read as well. So that's where this hexadecimal comes handy. You see that, okay, each number in decimal equals to 4 bits in binary. So it reduces the length of the overall number considerably by 4. Now, in binary system, which is base 2, there are only 2 unique numbers, 0 and 1. In base 10, there are 10 unique numbers, 0 to 9. In base 16, on similar lines, there are 16 unique numbers. And this table, if you look at, the first column is hexadecimal. And you see it goes to 0 to 9 just like decimal. But after that, it goes with some alphabets A, B, C, D, E, F, and the corresponding decimal is like 10 for A, 11 for B, C, 12, and so on, and there are 16 from 0 to 15. And if you want to convert into binary, since there are 16 unique numbers, so we need to use 4 bits at least to represent them. And so binary is represented in 4 bits. So you go with this 1 0 1 1 0 1 1 1 0 0 1 0 1 1 1 0, the similar pattern. And A is equal to, which is 10, is equal to 1 0 1 0. So weight, if you look at, is 1 2 4 8. So 8 and 2, this is 10. Similarly, you don't need to remember these ones. And if you use them very often, you will remember them anyway. That what is A is 1010, what is D 1101. But somewhere you can write this and it will be helpful. Now, if you look at hexadecimal has a notation of 0x in the beginning, then 9. So if you look at 9 over here is 1001, 1001. Let me do this. So if you look at each 4 bits, 1 2 3 4 4 4. So this is 9, this is C, this is A, B. Hopefully this is correct. Alright, so very simple, straightforward. I don't think there is any complexity there. Now we look into addition of binary numbers. Binary numbers, we're looking at 0 and 1. So we can have 0 0, and 0 1, we can have 1 0, we can have 1 1. So this is simple. 0 0 is 0, right? 0 1 is 1, 1 is still a valid binary number, so 1. 1 0 is 1. But when 1 1 in decimal is 2, but 2 is not a valid binary digit. So equivalent of 2, the way you write in 2, if you remember from the binary lecture, is 1 0. There's a weight of 2 here and there's weight of 1 here. This is 0, so the number is in 2. I think this one I did a previous video and felt like that was not recorded, so that's why you see still some rough notes from that. But I'm basically trying to do the same thing here. So if you look at, let me do that. So just was giving an example of take a different example. So in decimal, if you look at 7, 8, 15, we put unit 5 here, and when 1 carryover goes to the 10th digit location. So 1 is 1 by 10, which is 10, and there's a plus 5. So it's, we know this pretty well. So it's 15. In binary, 1, 1 is 0, 1. It's actually 2 in base 10, but in binary it's 2, which is the same thing here. Okay. Yeah, these examples over here, I already solved them because I thought I recorded a video, but it was not. But if you look at this 0, 1, 1, 0, 0, 0, 1, 0, it's a binary 2, it's binary system. So I'm mentioning here too. So add them 0, 0, 0. 1 and 1 is 1, 0. So 1 and 1 is not 2, even though it's binary. It can be very confusing for some people. 1 and 1, you don't put 2, even though it's a binary, but the valid numbers in binary are 0 and 1 only. So equivalent of 2 is 1, 0. So we put 0 here and 1 goes there. And 1, 1 again, 1, 0. So we put 0, the unit one. The next one goes as carry here. And so this is the answer. Another example, we look at 1, 1, we put 0 and 1 goes here. Then is 1, 1, 0, 1, 1, 1, 0, 0. So this is an interesting case. So our first number is 4-bit, second number is 4-bit. Now if we keep the answer as 4-bit, later on when we think about hardware, you will see that there's always a hardware line or something where we are having this logic level 0 or 1. So if we keep the answer in zeros, the answer is called overflow. So if you think of this is overflow, like 1, 2, 3, 4 bits, 1, 2, 3, 4 bits. So if you only consider them, then answer becomes 0, but actually we typically have detection for an overflow. So in this case, it's important that we know that answer has gone bigger than what we can represent in 4 bits. So 1 is here. Okay. Let's look at subtraction. This is an interesting case of addition. Again, let's start with an example because it's much easier to know with an example. We're looking at 5 minus 3. 5 is plus 5 and minus 3 is same as saying plus minus 3. So first we need to represent plus 5 in binary, then we need to represent minus 3 in binary, and then we simply add them. So first plus 5, pretty obvious, straightforward. Plus 5, we will go into this one. So already let's rub this out. Sorry, I'm taking a little bit time, but I think this would be good. And alright, give it this. So focus here now. Plus 5 in 10, we want to convert into binary. So we know that weights are 1, 2, 4, 8, 16. So plus 5 is written as 1 under 4 and 1 here, so that's the 5. So 0, 0, 1, 0, 1. Now let's look at minus 3 now, but before we create an equivalent for minus 3, look at plus 3. So plus 3 is again weights are 1, 2, 4, 8 and 16, right? So 3 is just 2 here and 1 here, everything else is 0. Now when we want to convert this into a negative number, this is plus 3 and minus 3, we have to create a 2's complement of plus 3 or 2's complement of this binary number. Again, if we want to convert, if we want to create a negative equivalent of this, we want to create a 2's equivalent of that. That would be the minus 3. But how we do that? So first we calculate 1's complement. And 1's complement is simply the inversion of the bits. So 0 becomes 1, 0, 1, 0, 1, 1, 0, 1, 1. And then we add 1. So this is 1's complement plus 1 becomes 2's complement. So then you add 1. So now you add this and this. 0, 1, 1, 0, 0, 1, 1, 1, sorry, 0, 1, 1, 0, 0, 0, 1, 0, 1, 1, 0, 1, 1, 0, 1. Now here is an interesting thing. I intentionally skipped in a little earlier. When we represent numbers in 2's complement, the most significant location has a negative weight. Again, in 2's complement, the most significant location has a negative weight. Like this has a 1, this has 2, this has 4, this is 8. This is not plus 16, but rather minus 16. So if you think of this, this is minus 16 and 8 and 4, 12 and 1, 13. So minus 16 plus 13 is minus 3. So this is really minus 3 even if you convert this into decimal. Alright, now we have converted this 2's complement, just put it here. This is minus 3 base 10 equivalent in binary and plus 5. Now this thing is minus. It doesn't matter for this case because there's no 1 here. So in the 2's complement, if it is 1, 2, 3, 4, 5 bits, what we do is 5 bits, the most positive number is this. The MSB has to be, most significant bit has to be 0 for positive. So this is the largest positive number. And the largest negative number is this. What is this? This is this number. 8421. 8412 to 15. So this is plus 15. And this minus 16. So you see in 5 bits, when we say 2 complement, it actually doesn't go all plus 31. It's not like that. This has to be 0. Only these are 1. So it's, if you want to generalize this, let's not confuse us more. Whenever I put those n powers and all that, it's complicated. Simply remember that if for 5 bits, your number is only positive 4 bits. And the negative most is this one. And why is that? If you put any number here, the number will become less than minus 16. Because if minus 16 will be added to this. So this bit becomes a sign bit. What to mean? Okay, now you got plus 5. You got minus 3. All you do is simply add them. 1, 1, 0. 1 goes here, 1, 1, 0. 1 goes here, 1, 1, 0. 1, 1, 0. Again, let me check that. Oh, we can check the answer too. This number is plus 2. And the beauty of 2's complement, even there is an overflow, it doesn't change the number. So if again you look at 1, 1, 0, 1 goes here, carry over, 1 goes here, 1, 1, 0, 1 carries over, 1, 1, 0, 1 carries over, 1, 1, 0 carries here. But we are 2's complement, so we are just using these ones, and answer is correct. Let's link it to another example. Okay, now instead of plus 5 minus 3, we're doing minus 5 plus 3. Answer should be minus 2. Let's check that. First of all, 3. 3 is this. Again, it's a 2's complement because we have a negative number involved. So this is minus 16, but 3 is just there, doesn't matter. Minus 5. And what was the step? First you create plus 5 equivalent binary, which is this 1 and 4. Then you create 1's complement. All you do is you invert the bit. 0 becomes 1, 0, 1, 0, 0 becomes 1, 1, 0. Okay, and then you add 1 to make as 2 complement. So 0, 1, 1, 1, 1. So this one, even if you check if into decimal, this is really minus 5. So what you do is you bring this number, this was plus 3 and this is minus 5, and you add them 1, 1, 0, 1 carryover, 1, 1, 1. Okay, this is a new thing. 3 ones. I don't think that happened so far. And when 3 ones, 1, 2, 3, in decimal we say 3. But the corresponding for 3 is, in decimal is 1, 1, 1, 1. So all you put 1 here and 1 here. And then it becomes simple, 1, 1, 1. And let's convert into decimal to check if it's correct or not. So this one has minus 16. So if you do that, minus 60 plus 14 minus 2, and that was supposed to be the right one. Hopefully I wasn't too quick on that. And if I'm quick, please go back. And normally I'm very slow, too slow sometimes. So go back and watch this video again. And if you have any questions, let me know on LinkedIn or ask me in comment. Thank you so much. See you next time.